This is the first of 3 videos about oscillating motion, simple harmonic motion. In this video we'll cover some fundamentals and discuss what is simple harmonic motion. What is simple harmonic motion? It's basically oscillating motion about a fixed equilibrium position. If you imagine the mass wasn't moving, it would be in equilibrium. Its displacement, we say, would be 0. As it is oscillating now vertically, then its displacement is positive, negative, etc. A graph of displacement against time would be sinusoidal. It would be a sine or a cos function. It would be sinusoidal. That's not a definition of SHM, it's a description of SHM. There's lots of examples in nature of things which oscillate in a way which is very similar, approximately SHM, and lots of man-made things which oscillate with SHM as well. Just the flapping of a butterfly's wings, the cone of a loudspeaker, the pendulum inside a grandfather clock, the string on a musical instrument, etc. Lots of things oscillate with SHM or very, very close to SHM. Equations that you should learn, very, very similar to the circular motion equations. One thing I would say is that omega, I wouldn't call it the angular velocity. I would just say that it's a constant related to the frequency. Even though it's measured in radians per second, just remember that omega is 2 pi f. Don't think of it as angular velocity. It's a constant related to the frequency. And omega is 2 pi over t, t is 1 over f. X equals a sine omega t. X is the displacement, a amplitude, omega the angular velocity, or rather this constant related to the frequency, breaking my own rule there. V is a omega cos omega t. More usefully, V max is a omega, because the maximum value of cos omega t will be 1. And then, very important, a equals minus omega squared x. So if omega is a constant, that tells us that a equals minus a constant times x. And this is a fundamental idea, and this is our definition of SHM. A body is doing SHM if its acceleration is proportional to its displacement and in the opposite direction, which is why there's a minus sign there. Note that agrees with the equation a equals minus omega squared x. If you look at this diagram of our mass on a spring, if we say upwards is positive, then if the mass has a positive displacement, its acceleration is downwards. If it has a negative displacement, its acceleration is upwards. Hence, the mass on a spring will perform SHM when you let it go, when it oscillates freely. These 3 graphs are very important. The first one, displacement against time, I've drawn as a sine wave. Velocity against time is a cosine. Acceleration against time is a negative sine wave. OCR, we usually have x equals a sine omega t. Just as a note, if you're doing AQA, then it's usually x equals a cos omega t. But notice that the displacement and acceleration are opposite signs. They're 180 degrees out of phase, or pi radians out of phase, and they are proportional. Here's a little question to do. A mass of 200 grams on a spring executes SHM with a period of 1.0 seconds and amplitude 3 centimeters. Given that its displacement is given by x equals a sine omega t, calculate these quantities. And basically, using the equations that I gave you before, you could pause the video now and have a go at these first if you like. Or you could cheat and just look at the answers. And there's the answers.